Okay, welcome everyone to my continuation of what are my favorite theorems. As usually, right, my favorite theorems, very biased point of view, take everything with a grain of salt. So what I'm going to talk about today is not really a theorem. It will involve some theorems, but it's not really a theorem. It's more like a philosophy, a meta philosophy, whatever. It's the so-called ADE classification um, phenomena. So it will turn out that a lot of things in mathematics, and mathematical physics, which are pretty much seem to be unrelated in any way or not related in any way, um, turn out to have the same answer. So different problems look completely different, have the same answer. This usually should tell you that something is going on. And it's not like it's not just like that two different problems have the same answer. It's even better because the answer is kind of something that always kind of happens in mathematics. We don't really know why. It's a certain type of answer in the sense that you have some infinite families of objects that you come up as an answer, and you have a funny finite number of exceptions or exotic cases. So the E here in my talk will be referring to kind of exotic cases in some sense. Um, Although originally I'm going to explain that the E never stood for exotic. But in some sense, these will be the exotic examples to a certain question. And they're exotic in a really good sense. They're exceptional and exotic in the good sense, meaning that they tell you something about hidden structures in nature itself. So this ADE classification, the whole point, I say it again, is that it connects various fields of mathematics and seems to be a very general kind of pattern of nature. It's something that always appears for different questions in different contexts, and it's it's just amazing. It's just really amazing. So let us have a look at three examples, and all of them will have an ADE type classification, although they look pretty different. And then at the end, I will list even more examples. I know about 20. I will only list 10 or so, but I know about 20 examples of having the same kind of classification, although they come from completely different fields. And if you be a little bit more vague by what you mean by an ADE type classification, then there are hundreds of more examples following kind of the same pattern. So this is really amazing and really weird in some sense, and we don't really understand what's going on. It's pretty good. So you have infinite families. In this example, it will, or in the example I'm going to present you, there will be the AD types, and you have those funny exotic examples, which are really important and tell you some hidden symmetries in nature itself. But let's do something concrete. So I would like to ask the following problem. So I take a graph, so this one, for example, looks pretty innocent, just a line. And I would like to ask kind of a problem, what is the easiest possible, are the easiest possible graphs? And easiest possible certainly is a bit vague, so we need to make this more precise, right? A line graph, probably, this one is a line graph. Probably most people would agree that a line graph is reasonably simple. So what I don't want is to include stupid examples, trivial examples. What I would like to exclude is graphs that are not connected. So something like just a random collection of vertices. Nah, I don't like that. If you understand the connected case, you will understand the non-connected case as well. What I also don't want is that a vertex has a loop. I also don't want that. So no vertex is connected to itself. You can build that in, but you still get an ADE type classification, but it's slightly more complicated. I don't want to do that today. But otherwise, just take any graph you like. Let's say with a finite number of vertices and edges, just to be sure. But anyway, any graph you like, and you ask the question, what are the simplest possible graphs? And yeah, so let's make simple precise. And the way to make simple precise is as follows. You observe that actually a graph is the same datum as a matrix. And the matrix, that's very easy to get. So it's called the adjacency matrix. Whenever you have a graph, so here's a very easy graph, just three vertices, and they're connected in the cycle. Then what you can do is, well, you certainly can give your vertices names, 1, 2, 3, and then you can assign a matrix to it by just looking what vertex is connected to what vertex, right? So which vertex are connected. So 1 is connected to 2 and 3, but not to itself. So in the first row, you write something like 0, 1, 1, right? 1 is not connected to itself, but it's connected to 2, it's connected to 3. 2 is not connected to itself, so in the second row, you write a 0 and a 1, 1, because it's connected to the others too. And similarly for the third one, and you get a matrix. So each graph gives you a matrix, it's called the adjacency matrix, and there's the same datum. Each such matrix gives you a graph. It's just really the same. The graph is basically an illustration of the matrix, if you want. Okay, but then we can have a look at our question again, because now we have matrices, and we know a lot of good invariants about matrices from linear algebra. The one I would like to take here is the largest eigenvalues, the so-called spectral radius. So just compute the eigenvalues of the matrix. There will be a biggest one when I take the absolute value, and it's called the spectral radius. It's rho. So rho will be bigger than any other eigenvalue of my matrix, considering absolute values, right? Eigenvalues are complex numbers. And you might ask, what are the matrices such that maximal eigenvalue is lower than a certain bound? And a certain bound that seems to be of crucial importance is the bound 2. For some reasons that are a little bit hard to understand, and we don't really know why. But the crucial bound here is 2. So easy question, what are the graphs with spectral radius strictly lower than 2? So what you need to do is you need to write down your favorite graph like this one. You need to convert it to a matrix. That's an easy step. You need to compute the eigenvalues of that matrix and pick out the biggest one. Computing eigenvalues of matrices might not be super easy, but for a computer at least it's easy. So I did this with a computer, and you get something like the spectral radius is about 1.88, which is good because we wanted that graph to count as an easy graph, and in this measurement it's an easy graph. Okay, now you manipulate that graph a little bit, so this still looks like an easy graph. The adjacency matrix slightly changes, so you have a branching here almost at the very end. So a branching at the very end would be a little bit boring. You would end up with the same thing as before, of course. But anyway, so you're at a branching at the next very end, and you compute the eigenvalue, and you get 1.95. Okay, still below our bound. You branch at the next point, get another graph, you get 1.99. That's very close to 2. So let's see what happens if you branch another one. You get another graph, and oh, sorry, you're below above the bound. Okay, so our complexity bound is graphs with eigenvalues, with the biggest eigenvalue being strictly lower than 2. And to check that for each specific graph, give me a graph, I can check, well, maybe a computer can check it easily because computing eigenvalues might be a bit tricky, but in principle, that's a very easy thing you can check. What is absolutely not clear is that this problem has a nice answer. I mean, you could have a very complicated and strange graph and could still have a small eigenvalue, small spectral radius. Who knows, right? Just writing down a list of examples is easy. Coming up with an answer is hard. And it turns out that it's even, well, you can prove it. So there's a theorem saying here's a classification, and the classification is an ADE classification. It's one of the good classifications that kind of appear everywhere in nature for some reasons we don't understand. So anyway, let me repeat. We have this problem. What are the simplest possible graphs? With simple meaning we want to have small eigenvalues. A seemingly completely different problem is to classify Platonic solids, or in a more modern language, to classify finite subgroups of SO3. So the special orthogonal matrices, orthogonal transformations of 3 space. Why is it related to Platonic solids? Well, because you can write down very easily a list of those finite subgroups. So each finite group is a symmetry of some regular polytope. And it turns out that under the assumption of having special orthogonal, you get the really regular polytopes, namely the Platonic solids. So in my notation here, there are three finite subgroups of the orthogonal matrices, namely the one that preserve a tetrahedron, this is this guy here, that preserve a cube, respectively an octahedron, so they turn out to be the same because there's duality going on. And the last one would be the ones that preserves the dodecahedron or the isocahedron. And yeah, those are finite subgroups of SO3. You can write them down. There are also others you can easily write down. There's this funny family of, well, you could think of having, like in this picture, having actually a regular polytope sitting here. So this has 8 vertices. So you can just think of having a rotation here in just a rotation in 2 space, nothing in 3 dimensions, just a rotation in 2 space. That works for any regular polytope and gives you a family of cyclic groups that are denoted by AN. So those are cyclic groups. Cyclic. And if you take now into the account that you live in 3 space, you're not just rotating, but you can also live in 3 space, then you get this family of these dihedral type groups called D, and there's a symmetry groups of these regular polytopes, which is just this regular n-gon with a dome upstairs and a dome downstairs, and this extra operation from here to here is actually just the reflection, the corresponding reflection along interchanging the two, the corresponding rotation, interchanging the two domes. And yeah, so here you have those are the platonic solids, as I said, and these are kind of platonic solids which were not considered by Greeks, by the old Greeks, for a reason that is not quite clear to me. But basically what they did is they ignored the diagon. So they only started from the triangle onwards. Triangle for them was a regular polytope. Square was a regular n-gon. Pentagon was a regular n-gon, and so on. And then you build everything out of those regular n-gons, and you end up with a platonic solid. But you can also start with a diagon. So this is a triangle, right? A trigon. And the diagon, so it has 3 vertices, 1, 2, 3. And the diagon is exactly what you think it is. There's 2 vertices and 2 edges. So a diagon. And for some reasons, they tended to ignore those. But if you would consider this one, and you take its dual, then you get something that looks like this. There's a lot of diagons that glue together at the boundary, at the north and south pole. A lot of diagons, and it's actually also a platonic solid in the sense, in the strict sense of being a platonic solid. Like everything is built out of the same regular polytopes, the same regular n-gons. The Greeks just never consider them, probably just because they never liked diagons for some reasons. Anyway, the point is, up to this kind of slightly strange symmetry group where you ignore that you're in 3 space, the first one, the other ones are actually capturing all the platonic solids, including the one that the Greeks ignored. And you might ask, well, you can check that these are all finite subgroups of SO3, and you might ask, are there actually more, right? So could there be any other finite subgroups of SO3? And they would correspond to similar symmetry groups of similar kind of regular polytopes. So you would have discovered more platonic solids. The answer is, of course, no, there are no more platonic solids, but it's not clear in at least in this formulation. Right, same pattern, you write down a list of examples. That's easy. To check that they fit is also not so hard, but to see whether there are any other examples, families of examples, it's not so clear. And it turns out that this is also an ADE classification, which I don't know how you feel, looks completely different from this question, but they have the same answer. It's kind of that's the whole point, right? Totally different looking questions have the same answer. So let's go to another one, which also looks completely different, and it turns up in, so this is classical geometry. This is kind of combinatorics in graph theory. What I'm going to show you now is more like comes up more like in applied mathematics by modeling population growth. And the idea is pretty easy. So you take a graph. Here's my graph G, and not to confuse it with the numbers which I will need in this example here, I just call the vertices A, B, C, D. Right before I called vertices 1, 2, 3, 4, 5, 6, whatever. But I need actual numbers now, so I just call them A, B, C, D. Don't get confused. It's just a graph. It's just a graph. And the population is now a choice of integers for every vertex. So here vertex A gets 3, vertex B gets 4, you get a -1, and you get a 0 here. So that's my choice. And the population growth or population mutation is now the following trick or the following operation. You choose your favorite vertex, 4, for example, B, for example, and you mutate on B. What does it mean? Well, it means the following. You write down the negative of what you see, and you add the sum of the neighbors. So here's a neighbor, 3, and here's a neighbor, -1. So you add the sum of the neighbors. And in this case, you get -2, right? -4, let me do it again. -4 plus 3 minus 1 is -2, I guess. And that would be a mutation on B. And the question you ask is now, okay, you start with a graph like this one, and with a very easy population, you just start with one person somewhere on a vertex. You have just label 1, and everything else is 0. And you just ask the question, well, does this population growth procedure stabilizes? So I allow you to choose any sequence of vertices you want to mutate, and the question is, does it stabilize? So here's an example. So if I do, for example, C, this vertex, I write down the sum of all neighbors, which is 1. I subtract 0, so I get 1. And then I can do the same trick for B. I look at the neighbors, 0 plus 1 is 1. I subtract 0, I get 1. I can do the same for A. I look at the sum of the neighbors, which is 2. I have nothing to subtract, so I get 2. And I can continue. And the point is, I can now go around the circle, and the numbers get bigger and bigger and bigger. So here I already have 5, 7, 4. Now I can mutate again at 4. I get -4 plus 5 plus 7, which is already 8. So numbers get bigger and bigger and bigger. You can just go around the circle and numbers get bigger and bigger and bigger. So the population grows without bound. So this is not an answer to the question of for what graphs do you get population stability. So population can't grow without bound. And it's, again, absolutely not clear why there should be any reasonable answer at all. If you play around a little bit, you might find some nice graphs which actually have stability. I give you a hint. They look very similar, like this one, for example. But to just write down a proof or a complete list seems to be very hard, and also quite different from those two problems, like spectral radius, finite subgroups, so platonic solids, more like a model, an applied math modeling of population type procedure. Why should they be related at all? It turns out they're very much related, and they have actually exactly the same classification. And that's the whole point. So this ADE classification, which I'm going to show you in a second, is just everywhere in mathematics. It's just so crazy. You look at completely different problems, they have the same answer. And this is, of course, telling you something important. And not just that they have the same answer, but kind of the exotic examples are very, very important structures in nature. In this case, here, the exotic examples correspond to platonic solids. Probably most people would agree that platonic solids are something important that you see in nature and in mathematics. Anyway, so here's the classification. So in this case, the theorem is the 3 problems from before, they have the same answer. And you can actually formulate it in terms of subgroups of SU3 instead of SO3. So you can also write SO3 here. then the subgroups look a little bit, so there is not much of a difference between SO3 and SU3. And I just wrote SU3 because I think in the link in the description, you will see it for written down for SU2, while I chose to use SO3 because, well, then I can talk about platonic solids. Anyway, that's just a technical detail. You can ignore it. But the point is, all of these three problems, spectral radius of graphs, finite subgroups, so platonic solids, and population stability, they have the same answer. And that's just crazy. And the answer is, well, you have three types of things. So you have an A, you have an D, and you have an E kind of answer. And the A type of kind of answer is kind of an infinite family of canonical answers that you would write down very, very quickly. So in this case, line graphs. So line graphs have a very, very small spectral radius. They are certainly easy. The line graphs in the other example was just the rotation groups that ignored just in two space that ignored the rest of three space. And in the last example, it's very easy to verify that line graphs actually satisfy population stability. Slightly more involved and usually coming from some symmetry of the line graph are this type D family. And there are again infinitely many of them. And in this case, it's very easy. You take a type A graph, so a line graph, and you have a slight branching point at the end. And you can make this as long as you want. You get another family. For example, in the example with platonic solids, it was this platonic solids that the Greeks missed, the one built from diagonds, and there are infinitely many of them, because remember that it was basically this picture, and it's like peeling an orange, and you can have as many of those cells as you want. So there are infinitely many. And then the funny ones, the type E ones, and there are only three of them in this case, and this really stops, right? That's the whole point. So there are only three platonic solids up to duality, and there are only three exceptional graphs where population gets stabilizes. There are only three of those exceptional or exotic graphs where the spectral radius is small. And that's strange. That's just really extremely strange. They're related to various questions which are important and have surprising answers. So a lot of surprising things have type E things associated to them. They're exotic in any good sense of the word. They want to tell you something funny about nature itself. Anyway, so the point is, again, this classification is kind of the best thing you could hope for. You have a family of examples you easily find. You have a family of examples which is just slight tweaks of the canonical type A type examples, and you have a finite number of exceptions. And not just that's the best you can hope for. No, it's also connecting very different fields of mathematics. So down in the description is a link with zillions of examples that have an ADE classification. Let me just discuss some of them. And now the details don't matter, just to give you a feeling that they turn up in really different fields of mathematics. So the classical one is from Lie theory. So Lie theory, that's where actually the name came from. So Killing tried to classify simple Lie algebras or simple Lie groups. And he wrote down, well, you have to massage it a little bit to really get an ADE classification. You get a slightly more complicated thing. And he just named them by the letters of the alphabet. He started with A, then there's B, C, D, E, F, G. Yeah, okay, just probably that was his only reason. Just, okay, why not? Why not start with the letters of the alphabet? Anyway, so that's why it's called ADE. So E is not really exotic. E is just whatever, the fifth letter in the alphabet. Anyway, we should really think about this as being exotic. So that was the starting point in Lie theory. And then you turn up in so many different fields of mathematics and physics. It's really, really strange and really beautiful. So they turn up, just to give you a few examples. I listed them. And again, I say it again. So more material is listed in the description below. And in particular, all of these examples are explained why they end up with the same classification. But it's kind of surprising. So you have something in algebraic geometry, singularities of surfaces. You have something in dynamical systems, so like fractal structures, elementary catastrophes. You have something in representation theory, curves of finite type. You have something in physics, so conformal field theories. You have geometry, Coxeter groups. You have combinatorics again, positive definite quadratic forms on graphs, and more and more and more. And I mean, conformal field theories and surface singularities don't, at least from my point of view, a priori don't seem to have anything in common. But no, they actually have the same classification in this sense. And this is just amazing. And in all of these examples, kind of the type E ones are special and they are very, very important. There's much more, as I said, linked in the description. A lot of things have an ADE classification, and this is just crazy. Okay, but basically that's it for today. So let me repeat. This ADE classification is kind of everywhere in mathematics. It's kind of weird. You have two infinite families, the canonical one, a slight tweak of the canonical one, and those exotic examples. And it's just so crazy. It's just everywhere in mathematics, and nobody really understands why, actually, I think. And if you are a little bit more flexible by what you call an ADE classification, then it's even better than almost everything has an ADE classification. A good example is, for example, some of you might know that, the list of finite simple groups. Kind of the same pattern. You have infinite families, the AD types, like alternating groups, cyclic groups, groups of Lie type. And you have this finite number of exceptions, the exotic ones, the type E ones, the sporadic groups, with the monster problem being the most famous one. Also, in some sense, an ADE classification. Like almost every good classification in mathematics is an ADE type classification. Anyway, that's it for today. I hope you enjoyed the video, and I hope to see you next time.